Okay, now that we have looked at an example of how a Earth system model called UVIC was used by the authors of this book to do some past climate simulations, let's look at climate variability through the last 135,000 years ago, which is the last glaciation. As we said already many times, Homo sapiens appeared around 200,000 years, and we've had 6 marine isotope stages. We will keep using these terminologies. Marine isotope stages are, of course, oxygen isotope signatures, and within that we will see that there are things called Dansgaard-Oeschger events, which occur right around 1500 year time scale. And then you have slower time scale variabilities called Heinrich events, which are the release of glaciers onto the North Atlantic where deep water forms, and they can affect deep water formation rates, meridional overturning, and we'll see how that can in turn have cascading effects onto basically at least Europe, but also onto the monsoons, Asia, and so on. So obviously the idea still is to try to see how many such perturbations to the climate happened at what time scales, and how they may correspond to the human migrations out of Africa, back to Africa, speciations, isolations, etc., etc., right? So this is a nice simplified figure that shows going back to 200,000 years. There was a cooling period. Remember again that O18, the way it works, if ocean O18 is getting concentrated, you can see the scale going down here. That means more of the O16 is getting locked up in the glaciers, so climate is getting colder, leaving O18 behind in the ocean, which is recorded in benthic foraminifera, which form calcium carbonate shells. So there was a cooling in the MIS6, which was potentially the coldest one in the glaciation that preceded the arrival of the Holocene. So MIS2 here, which is the colder of the 135,000 year period, was probably not as cold as MIS6, and this would have had a major impact on all the species of Homo lineage that were around at the time: Erectus, habilis, sapiens, Neanderthals, Devonians, Floresiensis, and so on and so forth. Make sure Erectus was still around. Maybe it was gone by then. But nonetheless, we have to see what the rapid warmings mean, and we have talked about how glaciations are slower timescale processes and warmings are abrupt timescale processes. And you can see even in this low frequency figure, you see many small cooling and warming periods happening, which means there were associated sea level changes creating new pathways, land bridges, and there would have been vegetation changes, rainfall changes, resource limitations or resource abundances depending on which way you are going, loss of species, megafauna for hunting and gathering, and so on and so forth. The book goes through lots of these periods essentially to take all the recorded evidences reported in papers to look at those isotope stages, and then does model simulations to fill in some of the gaps that cannot be obtained from observations, or to confirm some of the evidences gathered from sparse observations, all the proxies that we have been talking about. Okay, so this is again multiple evidences looking at sediments and various other uranium kind of evidences. I won't go into the details, but you can again see that this one has a longer term context going back to more than 300,000 years. So you will get a couple of glacial cycles here, coming out of the interglacial here into the glacial, going into the interglacial, coming to the last one that started around 135,000 years ago, and then got to its maximum by about 21,000 years ago. We started to come out of it. There were a couple of hiccups that we will look at, and then we got into the Holocene. And as agriculturalists and now technologists, we evolved basically in a time period where temperatures were fairly steady. So we have to compare the various stages, 6 and 2, for example. The coldest one that came at a critical time as Homo sapiens were beginning to arise and run around, and how they got affected by this steep deglaciation that happened, and then the glaciation that went on for some time with hiccups in the middle in terms of small deglaciations, glaciations, deglaciations, and so on. So which species benefited from it, which species were forced to migrate out and around, and so on and so forth, have all to be understood. And there are many details along the way that one has to be careful about. So if you compare again here Antarctic and Greenland. So NGRIP is a Greenland signature. This is a Antarctic signature. Multiple proxies are used. Delta O18. This is parts per billion. I think it's calcium, sodium. There is protactinium, and so on. But the main point I want to point out of this particular paper is that looking again at only about 70,000 years or so, the paper makes a point that when you look at CO2 signatures and methane signatures here, the green one here is methane, and this is the temperature. Here you are again noting all the Damsker-Ushker events and the marine isotope stages and the stadials and interstadials. So cold periods and warm periods with blue and gray shading here. The idea is that as rainfall patterns change and glaciation changes vegetation on land and ice cover on the ocean and so on, the way methane cycle was responding, which is related to land vegetation, wetlands, rainfall patterns, and so on, versus how the carbon cycle was responding at the same time. Carbon cycle can be with buried vegetation under glaciers, ocean changes because of dryness change in the atmosphere during cold periods and warm periods, and how that supplies micronutrients like iron to the ocean, and how that changes photosynthesis and drawdown of carbon in the ocean, and so on. Remember that my bloody computer keeps going off. This HP, every time I update the operating system, it begins to freak out. Okay, so those are the points I would like to make. So people have looked at the carbon cycle and methane, trying to interpret methane. Doing methane cycle simulations is not that easy, whereas carbon cycle we understand much more, and people have done carbon cycle simulations even going back to the Carboniferous using simplified models to understand how carbon has varied over time along with climate. We already talked about positive feedback of the carbon cycle during glaciation, deglaciation, decreasing during cold periods, increasing during warm periods, whereas on longer time scales, geologic time scales, changing temperatures and precipitation tend to provide a negative feedback with weathering rates changing accordingly. So we have to keep that in mind as well. So this is looking at the processes that potentially controlled the changes in methane and CO2. Again, tropical processes and northern hemisphere processes and southern hemisphere processes and combined scenarios, carbon loss and carbon gain for the deep ocean basin, Atlantic, Southern Ocean, Indo-Pacific, and so on. The point I'm trying to make again is that carbon cycle reconstructions have been done to try to understand what explains the recorded carbon variability during the last 6 marine isotope stages, because that also corresponds to processes that are relevant for human migration and evolution. If you look at the same thing after the deglaciation started 20,000 years ago, you can see that we obviously have increased methane significantly with some blips along the way. The processes of northern hemisphere and tropical processes, southern hemisphere processes, and combined scenarios have contributed to changes in so delta CO2 is change with respect to the base period. So obviously coming out of the glaciation, we went from about 200 ppm to 200 ppm by 280 ppm by the time we got to the pre-industrial period. So it's just a point that we have to track climate changes, vegetation changes, precipitation and temperature changes in specifically, and their impact on vegetation and so on. So people reconstruct potential vegetation, which means what is the maximum vegetation that is achievable given the climate conditions like humidity, temperature, precipitation, and seasonalities. So this is just a depiction that shows the European region for the present potential vegetation. Of course, this includes modifications by humans for agriculture and so on. So tundra, boreal woodland, closed boreal forests, cool temperate, moist steppe, dry steppe, wooded steppe, Mediterranean forests, and so on. And the idea is to compare to what happened during the glaciation 22,000 to 14,000 C14 years ago, which means that the dates determined by carbon-14 isotope that we talked about. So you would have had large glaciers, the Laurentide ice sheet sitting over here. I think Laurentide was on the US. This one is called the ice sheet. I will look it up later. So polar deserts, the cool temperatures would bring polar deserts, steppe tundra, open woodlands, dry steppe, and semi-desert. So you would have massive shifts in vegetation, obviously would affect human settlements and human movements, and force species to migrate, not only humans but also animals on which they would have defended, fish, and whatever other activities they were depending on for resources, water as well, and so on. So if Neanderthals were better suited for cold temperatures, then that would have affected the other Homo species differently, maybe driven them out. Maybe Neanderthals would have had an upper hand in the cold temperatures, but obviously eventually as the glaciation continued and became maximum at 21,000 years ago, Neanderthals had already disappeared. So Rheesiensis were still surviving in flores in Indonesian seas, and other species may have been around as well, like Devonians. So we have to look at those timelines again. But the main point is to look at climate change at as much detail as possible, corresponding to the migrations out of Africa into Asia, back to Africa, into Europe, and also try to understand the isolations, resource limitations, mixing of various species. If they are forced to take refuge in a small refuge, the refugia that we talked about before, then you will have mixing of genetic material as well. Okay, so let's leave it here and come back and look at more details of climate variability along the way.